This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So, today we'll continue introduction to the subject, just to introduce a few more concepts that are essential for the material that follows. Before we start, I just want to check, do you remember what we did yesterday? This is like a short-term memory loss test. Yep. So what was the conclusion? All right, so that's a very detailed answer. So open loop, is it better than closed loop? No. For what reason? Doesn't handle disturbances, model uncertainty, and things like that. So we will stick with closed loop most of the time in this subject. And we said open loop has its place, but feedback does help in terms of uncertainty. If you remember, we talked about op-amp example as an example where feedback provided necessary robustness for the system to work. So today we will talk about more detailed concepts that or features that, of any well-designed closed-loop control systems. So we will introduce concepts such as equilibria, stability, concept of stability, transients, and also performance/robustness. So each of these will pop up in every design that you will do in this subject. So whenever you're dealing with a problem, you would need to model it. Typically, models are nonlinear. You would need to find equilibria, then maybe linearize around that equilibrium. We will talk about linearization later. And then you will need to design your controller so that its closed loop satisfies stability. We usually design stable systems. Then you would be interested in transients because different transients may lead to different behaviors, and some of them are acceptable and some of them are not. So you need to understand what are the acceptable transients in different situations. And then you will also look at performance, and in particular we're interested in robust performance. So each of these will be a recurring theme in different lectures throughout the subject. And we will, in these lectures, simply introduce them and present a few examples to illustrate these concepts. So here's the outline of the lecture. First, we'll talk about equilibria, then stability and tracking, transients, performance and robustness, and conclusions. So we will dedicate a few slides to each of these, in some cases present examples, and just sort of try to get the intuition behind these concepts. Later on, they will be mathematically precisely defined, right? But in this lecture, it's just sort of, I want you to get the intuition right. All right, so what are the basic properties that any closed-loop system or any system should really satisfy when you design it? Well, desirable steady-state behavior needs to be achieved. In other words, equilibria need to be like the behavior that we are interested in needs to be maintained, which leads to the concept of equilibrium. So equilibrium in a system is an operating regime that can be maintained for all time. So, for instance, in the room temperature control example, if you can maintain, 25 degrees in the room or 18 degrees, well, that's an equilibrium. So an operating regime that can be maintained, it's an equilibrium. We will talk about that in more detail later, but we are definitely interested in equilibria. Then desired steady-state behavior needs to be attractive. So if I design my controller so that equilibrium of 25 degrees in the room is of interest, you would want the true temperature room to converge to this equilibrium. So you set the equilibrium you want on the knob on the wall, that's the desired temperature, right? And then you want the system to control true temperature to this desired temperature. Desired temperature denotes the equilibrium that you want to be attractive to, okay? Then transition to steady state behavior needs to be appropriate. In other words, transients have to be appropriate. If you have a control system that takes 2 years to heat up the room from minus 20 degrees to 18 degrees, it's unacceptable. You will see that we would characterize transients of general systems, and each different system would have different requirements on transients. But in this lecture, we will introduce some of the features of the transients that we might be interested in any control system, right? And then desired operation needs to be maintained despite uncertainties and disturbances. We already saw in the open loop versus closed loop lecture that disturbances can really affect your system adversely. And we want to have operation that is good, acceptable, even if there are disturbances, even if there are uncertainties in the model as well. And we will talk about that as well. So actually, any well-designed control system would have to satisfy all these in one form or another. And typical design would be that I tell you which equilibrium I'm interested in. Obviously, stability and tracking needs to be satisfied. I tell you what transition or what transients I want you to achieve, and I want you to also achieve this under disturbances. And that basically gives you a set of specifications that you need to take on board when designing a control system. And you need to achieve those. Your boss comes and tells you, I want this transient. You need to be able to design a controller that achieves that. Or you go back to your boss and you say, it's impossible. We will learn that there are some fundamental limits to what is achievable. I mean, with all best intentions, if I want to run a 100-meter, race in the Olympics, I won't get, even qualified, even though I want to, So give me the best coach, they give me best control algorithm, best training. There's no way I can do that. So there are some fundamental limits to what's achievable with your system. And you will learn how to identify those fundamental limits, right? So that's part of material in the subject. So this is like a very high-level introduction to all of these basic properties. And as I said, when you do design, you will need to look at each of these. All right, so let's now go through all of them one by one. So what are equilibria? Equilibria are related to steady-state behavior. So you probably would have your own interpretation of an equilibrium, right? So what would be, in your own words, an equilibrium? If someone is or something is at an equilibrium. I would use the word stability in a very different context, right? So here, stability, I would not use that word to describe equilibrium.
And achievable operating point?
Sorry?
Achievable operating point, something your system can do?
Yes, but I need more information. If a system can jump like this, is that an equilibrium?
Not jump exactly. It depends. If you're looking at the jumping rate, it can maintain that jumping rate, then that's an equilibrium. Depends on the system.
Okay, very good point. So some variables may be still constant. What you want to have is that physical variables in your system are constant, maintained constant. They don't change. So that's an equilibrium, right? So everything is at rest. There's no change. So stability is a slightly different concept. So we will actually talk about equilibria that are stable or unstable. So that's why I didn't like the word stability. All right, let's look at this in more detail now. So here is a mechanical system which should explain the intuition between equilibria. different types of equilibria, actually. But look, if I leave this ball in these spots, in a hole or on a flat surface, completely flat surface, or on this bump, right? If ball can stay there, if I put it there and it stays there forever, you can say that's an equilibrium, right? Here's another mechanical system. If I suspend this, stick like this, well, this is an equilibrium. But also, if I'm able to maintain it in the vertical position, if I just leave it there without any sort of influences and it stays there, that's another equilibrium. Now, you can see that these two equilibria, intuitively have very different properties. They look very different. One, if you push this ball slightly, then it would come back. Here, if you push it slightly, it would stay there. It won't go too far, but it will stay there. And here, it will just roll off to infinity. So that's actually related to the concept of stability. But each of these, as drawn on this figure, are equilibria and examples, because all physical variables in the system are maintained for constant for all time, right? So that's the intuition. Let's look at some examples. So if I have a water tank and I pour water into it, and there's some water flowing out of it, so the level of water or liquid in the tank will change. So let X denote the level of water in the tank. Well, depending on how much flows in, if more flows in, the level would rise. If more flows out, the level would fall. But note also, typically, this outflow would depend on the level. The higher the level, the more outflow there is. In any case, let's just consider the case when perhaps I can fully control Q0 by attaching a pump or vent so that I can maintain this level as I want, right? Let's look at this situation a bit more mathematically. So if I assume that the liquid is incompressible, then I can apply the law of conservation of mass, which then becomes law of conservation of volume. So basically, the change of volume of water or liquid inside the tank, so this dV dt denotes derivative with respect to time, right, would depend on the difference between the inflow and outflow, like volumetric flows. I'm talking about volumetric flows here. So moreover, if I assume that the cross-section of the tank doesn't change with X, like you have just constant cross-section, then I can take the area of the tank A outside, because the volume inside the tank is area of the tank then times the level. So I just take A outside because it's constant, it's independent of X, and then I have just this A dx dt is equal to this. So how would we mathematically, denote or find an equilibrium in this system? Well, if the inflow is equal to outflow, then the level doesn't change. That would be one definition of an equilibrium. So if Qi is equal to Qo, 0, that's basically the difference is 0, then we have the derivative of the level, x, right, with respect to time is 0. But what does this mean? Well, if I integrate this equation from some initial condition, I find that the change of x with time t, is, equal to x0. It doesn't change. So x of t is all the time equal to x0. So what I did, I just integrate. I took dt outside, here, so 0 times dt is 0. I integrate that from 0 to t, and then I get this. Does everyone follow this? Yeah, so it's a very simple example, but this shows, one example of equilibrium. If inflow is equal to outflow, I can maintain this level constant, right? Now, obviously, I didn't tell you anything about how to regulate Qi and Qo to achieve this. So if I have pumps on both sides, I can actually totally regulate them as I want. Then the outflow would not depend on the level of water in the tank, because I can, regulate the pump, how it works, how much water it takes out. And I can just close it down. So I can make Q outflow like 0, right? So what's important here is that we are now linking mathematics to a concept. I told you Conceptually, equilibrium is, an operating regime that we can maintain for all time, but I just mathematically modeled, in this case, what it means for this example. We will learn how to do this for much more general systems. This is just an example. Let's look at some examples. Like this is a very cool example of a water clock. So Thespios water clock, old maybe 2,500 years. So people at that time already used control theory. Maybe they didn't understand the mathematics behind and why it works in the way it works, but they managed to design these systems that had self-regulating properties. So what does this water clock do? Well, look, you have this float chamber here. Well, this pipe here is connected to some, I don't know, lake outside the city, and water level in the lake can oscillate depending on the season. Maybe it's lower or upper, depending if there's more rain or less rain. So the pressure just before here, would be varying. That's a disturbance, right? Now, this device turns out to be able, if designed well, it can regulate the outflow of this chamber, right? This chamber is actually enlarged here. So this is a zoomed-in version of the chamber. So water flows in from the top, but then there is this float inside. So for instance, if there is more pressure on top, so there's more water in the lake where water comes from, then there will be more inflow here. But then the chamber would fill in here, and this float would push the vent. It closes it down. So if it's designed well, you can make it so that the level of water here is maintained pretty much constant despite the disturbances, how much water there is in the lake. That's a cool invention, very cool invention. And what you get is that the outflow, you can assume that this outflow here is pretty much constant despite of how much disturbance we have in the system. It's a very cool device, right? It's like a, flush toilet on steroids. I don't know, like it's really like cool. But people use this, thousands of years ago. So now that you've achieved the constant inflow of water into this tank, know that this tank would typically have this vent that's closed whenever this is supposed to measure time. And then, since the water inflow is constant, the cross-section here is constant, then this float here would raise at a constant pace. So it's proportional, it's basically movement, upward movement is proportional to time. And we will analyze this mathematically in a moment. I, encourage you to understand this block diagram. I don't want to go into this block diagram. We already learned what block diagrams are supposed to represent, but I want you to sort of, on your own, go through it and sort of understand how, this system, this chamber, is sort of represented by this diagram. Let's analyze, so I leave this for homework, but let's analyze now what happens with the big flow chamber. So if we, achieve with the flow chamber that Qi is equal to Qo, right? Well, we will get roughly that the level of water in the float chamber is constant, right? So that would give us, constant, outflow. I mean, all of these things are related, right? So you will get constant outflow, and then, the outflow of the float chamber is constant, but that's the inflow into the big chamber, because outflow of the float chamber flows into the big tank that's supposed to measure time. But we close the valve in the big tank, so there's no water flowing out. So then we are using the same formula, but now Q is constant, right? So output is 0, and this Qi is constant. It's equal to Q. If we integrate the same equation now for the level of the large chamber, it will change linearly proportionally with time. If initial level in the big chamber is 0, then the current level is basically the inflow, which is constant, times time that elapsed. So basically how this thing would change, so this level here, well, it would just grow at a constant pace. And then this little, statue would point, what time it is on this water clock. So what we did here was we used the concept of equilibrium and we showed how, maintaining all variables constant, in this case, helps us achieve something. So the goal in this case was to achieve, measurement of time. And this is how it was done. But we did that by, maintaining this flow chamber level constant, despite of fluctuations in the input pressure, right? Are there any questions here? No? All clear? We are still at the level of intuition. I just want we are seeing a bit of mathematics, but this is more about intuition, introducing concepts. All right. All right, we covered the first one, tick off, right? So equilibria, we sort of have some intuition about what they are. We saw some mathematics, how we can calculate equilibria in one example. Let's look at stability, right? So that's another important feature of pretty much any control system you can think of. So what is stability? Well, all solutions would either converge or diverge or maybe stay close. Maybe not diverge totally, but they sort of stay close. If you start close, you stay close, but you don't diverge or converge. So we can broadly classify all systems or all equilibria of different systems into stable, unstable, depending on properties. We can also talk about marginally stable or like almost unstable or almost stable systems. So most systems that we will design would be required to be stable. So here is now the same picture of all these different equilibria, but now I can add an extra descriptor to each of these different equilibria. You can see that they all look different, but actually their stability properties are inherently very different. So this I would call stable equilibrium. Why? Because if I push this ball in any direction and then leave it to itself, it would oscillate, and then due to friction it would eventually converge to this point. If there is no friction, I would keep oscillating. Then it's not stable and attractive. I just am using here friction, dissipates energy, and you sort of, which is a realistic model, right? Eventually you will have this behavior. Here on a totally flat surface, if I sort of push this ball a bit, or if I just start it, so suppose this is the equilibrium I want, but I start ball from here, initial condition from here, and leave it to itself, it will never converge, but it will never diverge. So I would call this is like marginally stable system. And then here, obviously, if I just start this ball like anywhere here or here, it will never converge. It will just go away from the equilibrium that we want, perhaps. So this, again, is an unstable equilibrium, and this would be stable equilibrium for the pendulum, right? So if I push it, it just comes back, right? It quickly stabilizes, right? So you can have a range of different examples. In a cruise cruise control example, you set the desired speed. If the car is unable to maintain that speed, or if, under some disturbances like a slope up the mountain, if you can't maintain it, well, that equilibrium is not stable then, right? So we inherently, want to design systems that converge to some steady state operating regime most of the time. In many cases, that's the case. All right, so as I said, it's typically required for most control systems. We will learn mathematical methods, and in particular, Laplace transform would be particularly elegant approach to check stability. So we will be able to check whether an equilibrium is stable, marginally stable, or unstable, in the sense that I described in these examples. So often stability is not sufficient. Why is that? What do you think? Why would stability not be sufficient?
In a marginally stable system, we saw that we did not get the equilibrium we desired. So we can't track the output, basically. We don't get the output that we require.
I didn't get that, sorry.
In a marginally stable system, in your previous example, we saw that if we give a disturbance, the system remains stable.
Yes.
But it does not reach the point that we need.
All right. True, but why, even if you have the first example, where you have that things converge, why stability may not be enough? Why stability may not be enough? Sorry? Transients, exactly. You know, I mentioned transients before. In room temperature control example, if you have that your temperature does converge to 18 degrees that you want, that's your equilibrium you want, it does depend, you know, like whether the system would be acceptable or not. It depends on how temperature converges. If it's too slow convergence, it's no good. If you turn it on now, you know, and then you have to wait for 2 years for it to converge, it's not good. If you find that the temperature overshoots, you say, I want to go to 18 degrees, but it goes to 200 before it converges to 18, that's no good. If it converges to a point that is close to 18 degrees, but maybe too far, then that's not good either. So there are lots of features of the transients that will affect, you know, the performance of your system. And typically, you would get some specifications in terms of what's acceptable performance for your particular example, right? For your particular example. In some examples, you would want fast convergence. In some examples, slow convergence is acceptable, right? In some examples. So we will need to look at transients much more carefully. So stability is sort of necessary. You can think of it as necessary, but not sufficient for good operation of the system. So that's why we want to talk about transients. All right, so here is, you know, typical sort of test that we do in control systems to define what we mean by transients. So suppose that your system was at rest, right? It was at some equilibrium. And then you apply to this system a step input. What I have here is this signal was 0 up to time 0, and then it's some constant, let's say 1 after for positive time. Why is this test signal so interesting to us? Well, this corresponds to you saying, all right, I want my temperature in the room to go from, you know, 10 degrees to 25. And that's exactly the step signal. It was 15 or 10 degrees, and then you change it. You can approximate that signal as a step signal. So we are testing control systems in this way, and what we do then, we observe what would be the output. The output in the room temperature example is the true temperature of the room. This would be the desired temperature, right? And that's a step signal that you set to the system. That's the test for your system. And then the system responds in this way, right? So we can look at that response. So the temperature would change as time goes. By the way, this is time axis, and this is the value of the temperature, right? So we are interested then in features or characteristics of this response. So we are interested in features of this guy. And that's basically called step response. When we apply step input, what we get at the output is called step response. So transients are typically characterized in this way. So everywhere here we suppose that the system is stable. So system operated in one equilibrium, and then we change the reference. That would create a different equilibrium in the system, but we want all these equilibria to be stable. If they are unstable, these things would just blow up. So this sort of transients would occur. They would look like this only for stable systems. If you have an unstable system, it may just diverge forever. So it doesn't make sense then to talk about features of the transient response. So here is a typical step response. This is like maybe the most complicated step response. You know, well, it's not most complicated, but it contains all features that any response can have. So note that if I tell my system to go from 0 to 1, which is like desired value, right? That the input is, you know, step signal. What the true response might actually decide to go in the opposite direction. This is called undershoot. This is called undershoot. So where would this undershoot be present in true systems? What do you think? Can you give me an example of a system that exhibits undershoot?
Bicycle.
Sorry? Bicycle. Why? Very good.
You click in
Exactly. So if you think carefully about how you ride a bicycle, actually this is best observed in motorcycle races. You know, when they want to turn right, they first move very much to the left to take the right turn. So if you see how they follow the track, you know, they would be going to the left if they want to turn to the right, right? Sorry? Shifting to a fast gear. So when you are uphill, right, you might go backwards, perhaps. Maybe that's a good example. So you want to go forward, but you actually, if you're on a hill, you would sort of go backwards and then you would move forward. If you, for instance, you sort of lit a fire and you want fire to burn, more, you put coal or wood on it. First, this wood would suppress the heat, like until it catches up. So that's another example of undershoot. I love, the example of Zoolander. If he wants to turn, to the, left, he goes to the right? So that's an example of undershoot, right? So, okay, so we just did the undershoot. Now, note that this response here converges to this y, to this value y infinity. Now, this y infinity is basically potentially equal to the desired value where we want it to go, or it may be slightly off. Now, this difference between the value where we want it to go and where it actually ends up in steady state is called steady state error. So, if you look at this response, you also, by going to y infinity, you overshoot. There's this sort of bump on top. That's called overshoot, right? And then you can also talk about settling time. This TS is settling time. This is the time needed for the true response to get to within some margin from the infinite sort of steady state value. So maybe you can say, how long does it take for my response to be within 1% of the steady state value? That's the time, and then stay there forever. That's the settling time, TS. Now, rise time is defined differently in different textbooks. By the way, different textbooks may use slightly different definitions of these features, and mathematics behind then might be slightly different. So always check what sort of definition they use, because that would determine what sort of mathematics you end up with. So what is the rise time? Often, it's denoted as the time needed to go from 10% of the steady state value to 19% of steady state value. So rise time is in a way measuring the speed at which our system would respond, right? By the way, each of these different features, are independent of each other in a sense that you can have a system that has small rise time but very large settling time. You can have a system, like there are all sorts of different situations, right? You can have system without undershoot. You have systems that always have undershoot. No matter what you do, that's a fundamental limit. The system would always have undershoot. It's impossible to have no undershoot response, right? So you will learn these fundamental limits to certain systems. If I give you a certain system, you would be able to say, well, if the system model has these features, then it must have undershoot. And if your boss came and told you, all right, I want you to design a control system so that you don't have undershoot, you use the knowledge you gained from this subject and you say it's impossible. So you are asking me impossible. It's very important to understand what's possible before you start designing your system. So we will learn all these things throughout the subject. Are there any questions here? Yep. So for settling time, very good question. Note that I denoted here y infinity plus delta and y infinity minus delta. Y infinity is the steady state value. That's where your response would converge. And then you're saying, well, let me look at maybe 1% or up and down. of the y infinity, or 5%. So settling time is related to this delta, how much margin you are interested in. And different authors define settling time in different ways. Or they may define it in a general way by saying, well, for 1% margin, or this delta being 0.01 of y infinity, then settling time is defined in this way, right? For delta 5% of y infinity, settling time would be different, right? So settling time is intimately related to delta that you choose. Which delta is best delta depends on the application that you consider. It is very different whether you are designing a controller for, let's say, a very slow system, right? So there may be some systems like in biotechnology. So you may have a biochemical process. You are brewing beer, right? So you're brewing beer and there is a biochemical process. That takes time. May take, hours, days. Or you are, fermenting wine or doing something that's slow. Well, then, your specifications that you will put on the transient, desired transient for the system you want to design will be different from when you are designing systems in, let's say, nano scale. If you're trying to control something that is very, very fast, then obviously your transient that you want to achieve would be very different from a process that's very slow. So what we will learn is to basically say, all right, here is a transient, and in this particular situation, it makes sense to impose these conditions on rise times, overshoot, etc., etc. And then you would learn how to design this controller to achieve that. Typically, that would be appropriate for the problem at hand. Okay, that's how we use this sort of transients in design. Any other questions? Yeah, I forgot to use the parenting example, but it's obvious. You tell your kid, so what's undershoot? You tell your kid, to study hard because, to get a job, and they end up doing drugs. That's undershoot, right? You tell them to study hard, and then they study so hard, they don't see anyone, they don't have a boyfriend, girlfriend, that's overshoot. They are going in the direction you told them, but they are overshooting. And that's also not healthy, right? Or you tell them to study hard, but they decide first to take a gap year or a few. They end up in Bali for a few years. Rise time is long, right? Or they take, 10 years to graduate a degree of 2 years, right? That lasts normally 2 years. So that's basically settling time, right? So all of these you can really relate to any sort of dynamical process that you can encounter anywhere, right? All right, so what I didn't talk about is the fact that we will be able to translate these performance specifications on transients as mathematical requirements on the controller design. We will learn mathematics to precisely encode these requirements, and then you will be able to design controllers that achieve those in the closed loop system. So it's a very cool set of tools that we will learn. And these will rely heavily on Laplace transforms and also on frequency domain analysis. Often, Fourier transform is used for various analyses. And what we will also learn through these mathematical tools, that there are indeed some fundamental mathematical limitations to what's achievable. And you will learn how to recognize these fundamental limits, or how to design a system when you can actually achieve certain things. You will learn how to design a system that does achieve these things. We will use mathematics. I really don't like when I hear some students say, this is a very mathematical subject. This is actually a very engineering subject. It's all about design. You will use mathematics for purposes of engineering design. And yes, you need to learn some and understand some mathematics, but it's all about engineering design, okay? And I think it's cool. I love this stuff. I mean, I've been doing it for 30 years, and I'm still fascinated by by, yeah, I'm that old. So, all right, so let's just go through the last one. Performance and robustness. So performance can be measured in different ways. But, one, possible way is to say, well, I want everything to work still well, pretty well, if there are perturbations. That's sort of robust performance. So I will give you here a sort of typical block diagram for a control system, where I was more careful about different inputs that enter the system. By the way, we've seen already that feedback or closed loop system have this sort of feedback loop. Note that this is the reference, this is my desired signal. That's what we want the output to be. And then we have a feedback controller that takes the error between the true output and the reference, but there are no disturbances, right? And then processes it, that's the brain, and then it sends the control signal to the actuators that controls the plant model. And then something happens in the plant, and that changes the value of the output. So if everything is well designed, you will have that Y really tracks R. So this is your desired temperature that you set on the wall, and Y is the true temperature that actually the room, that happens in the room, right? So now what is new in this block diagram are these couple of, well, three actually, inputs. This input, that's sometimes called input disturbance. This input, which is called output disturbance. And this input that's called noise. They are new things that you haven't seen before. I will talk about these a number of times when we start looking at mathematical details. But at this time, just trust me that many control systems can be modeled in this way. So, for instance, what would be, in room temperature example, what would be the input disturbance? What do you think? So, by the way, input might be, all right, we can say that the amount of heat that the heater releases into the room, that's the control signal. Let's think about it in this way. So what would be then potentially input disturbance?
Opening the door.
Sorry? Opening, closing the door. So some heat goes out, So that's one example, right? You can think about different examples of control systems, and you can think about all of these different disturbances. Typically, we would think of this output disturbance as being slow in frequency, like doesn't change often, right? Doesn't change much. Whereas this noise, this N, is something that has very high frequency. So this is maybe you're using a sensor, digital sensor, and when you look at the sensor, the temperature on the sensor is just sort of oscillating around some value. So that's noise. That's sort of just noise, and typically, this is much higher frequency than any of the other inputs into the system. Note that this guy here is inherently very different from the rest. Why? We set it. We can control R. That's the reference that we control. Whereas all of these others are usually just, it's God's will, right? So they just are there because, they're just there. So what we would like to do often, and I will now say something which you may not understand at this stage, but I feel you can rewatch the lecture. So when we cover enough material, what is interesting is, think about this. What is this symbol here? It's comparator, right? So it basically just takes this signal, adds them up. So I can actually take this comparator and move it all the way here, whoop, here. So what happens then is I can write here R plus or minus N, R minus N. I can replace N and R separately as R minus N. Now, here is a sort of a cool question. Obviously, we want to follow R, but what I'm dealing with is R minus N. So how do I get rid of N and follow R? Sorry?
You can use a filter, maybe a high pass filter, a low pass filter.
You could do that. That's true. But if I don't do that, if I just say, okay, well, I want now, I'm dealing with this thing which is just r minus n. I want to follow r, but don't want to think about n. You are hitting the true issue, the frequency. Noise is high frequency typically, whereas r is typically low frequency. If you wanted to follow r, which is of the same frequencies as n, good luck to you. Right? So I can't help you there, put it this way. But don't tell anyone, I might lose my job. So no, seriously, in many situations, you exactly are dealing with this situation where r is low frequency, n is high frequency. So you want to reject n, but you want to follow r. And you can do that, and we will learn how to design control systems that are insensitive to noise, but they follow references. And the frequency domain analysis will help us achieve this. This is the really cool sort of outcome of us learning body diagrams, Nyquist criteria. And people will say, well, that's mathematics. Well, it's not. You really can design cool things. This is magic, right? But seriously, just think about it. If you took technology that uses control, I mean, I saw robots playing table tennis and winning, right, against top players, right? So if you took that to medieval times, you would be more popular than Harry Potter. Like it would be. It's a cool thing. So this is magic. You design magic. All right. So frequency domain methods will be used to shape the system frequency response to yield good tracking at low frequencies, which is basically reference signals, and then good damping at high frequencies, which is basically suppressing the noise. So then Fourier transform methods will be used to achieve these performance robust. It's really, I shouldn't say Fourier, I should say frequency response methods. We will learn about these a bit later. All right. So what I want you to take out from this lecture is really intuition about various characteristics of the closed-loop systems. So typically, closed-loop systems need to satisfy some basic properties. You need to be able to maintain some behavior that you are interested in. That has to do with equilibria. You would need to achieve stability or tracking of this equilibrium. So basically, all solutions should converge to this equilibrium or close to it. You will need to satisfy certain, constraints on transients. Your boss tells you, I want this overshoot, this rise time, design a system. You need to be able to achieve that. And then you need to do all of the above while respecting, robustness, performance requirements. So we will always use model-based design and analysis methods, but models are never exact. They are not exactly modeling the true system. There's always an error between the true system and the model. We design using the model, and then we implement on the true system. So there should be some inherent robustness in your design, so that when you take your controller that works well with Simulink and you implement it on the robot, it still works. That's robustness. That's what robustness is. So this subject will provide systematic tools for analysis and design to achieve these properties. And that's fascinating. I don't know, maybe you just want to go for coffee or whatever after this, but I'm just fascinated. So at this I would stop and just take any questions before we leave. Yep. Yeah, I mean, for instance, if you have, instability would typically require that some physical variables blow up eventually. Typically, things will burn out or break or something will happen, right, before you get this instability. However, it does depend also on which variable you are considering. For instance, you might have that you have like a ramp signal or something in your system, and then maybe like that may be your desired behavior, and you may be making an error, and you are sort of departing further and further. You have to think of, okay, when would that be desirable? I mean, instability can be useful, for instance, in cases when you have fluid mixing. So imagine you have two fluids and you want to mix them. You are mixing paint with, thinner. And you want to have uniform sort of mixture. There, you want to get turbulence and mixing to be as strong as possible. That's one example, like roughly of, getting sort of unstable behavior. But, or just sort of explosions, right? You drop a bomb and, it just sort of explodes. But there is a limit to how far these physical variables go. Your models may tell you that physical variables can grow unbounded, but in reality they can't. So instability has to be sort of interpreted also in terms of how good are models. So we are talking about stability or instability of models. So things blowing up, then your model would become invalid, and then there will be slightly different behavior from what your model predicts. So there are all these issues. Yeah, you can think of some situations where, that may be desirable. Yeah. Any other questions? No. Thank you.